Okay, here is a question about a plasticine blob in a box. Box is of mass m. This plasticine is of mass m. The spring is of k, and when this releases, becomes detached, the box moves up, and it strikes the bottom at the same time that this has come to rest at the top of its oscillation, its simple harmonic oscillation. And it's saying to itself, the system continues to oscillate, but then it has a different frequency, because of course there is a different mass as a joined mass. So, first question is, for this to happen, show that the internal height of the box must be yay. And I suppose, to give you a hint on how this works, you need to consider, for number one, the height of drop plus the change in the extension of the spring. And if you add those two, you should yield that. So I'll give you a little time to think, but otherwise, here comes the solution. Okay, what is the extension of the spring? Well, first of all, the extension is going to be the force divided by the spring constant. You're told this has a spring constant of k. You also know that the weight is m, so this is going to be mg over k. That's the first extension. So once that's removed, that's where the new position of equilibrium will be. But this is still moving up from there. So in actual fact, that extension, you're looking for twice that, 2mg over k. So that's the first bit. Now, what's the height of the drop? Well, you know that this thing is moving down and falling. The distance s is going to be ut plus a half at squared. We're going to use that kinematic. Of course, it started from 0, so you can ignore the first bit, but that still leaves you with a half g's acceleration t squared. What is the time period of oscillation of this thing? Well, the time period of oscillation, you should know, is 2 pi root m over k, where m is big M because we're looking at the time of oscillation of just this. This has become detached from it. It's moved from its lower position to its highest most position, so that's half a cycle. So the time period of falling is that divided by 2, which in fact gives us pi root m, big M, over k. Substitute that into there, and that yields us a half g pi squared m over k. And then if we merely have an addition of those two, put those two together, that gives us the height, which is 2m, the height, which is 2mg over k, plus pi squared mg over 2k. Tick. Okay, what's the next one? Write down an expression for the final frequency of oscillation of the box. Well, hopefully you're happy with the frequency being 1 over the time period, which gives us 1 over 2 pi root inverted k over m plus m, of course, because you're now dealing with the addition of the two masses joined. The same k. I think that's a fairly straightforward one, that one. But the next one requires a little bit of work. It says, what's the initial downward speed of the box after impact? Hence find the amplitude of the motion. You give your answer in terms of. So what's the hint for this one? So let me give you a few hints and then you can try it for yourself. First one, this is a momentum issue. And with that in mind, let's think about, let's just tackle one bit at a time. So the initial speed of the box is a momentum issue. Okay, I'm going to need a spare bit of paper to deal with this one. So what do we have? We have this situation, we have m, small m, and big M, and at the top, big M is stationary, small m is moving, let's say with v1, and that will result in, afterwards, both of them moving at speed v2 after the collision. Okay, very straightforward bit of momentum theory. Momentum before the collision must equal momentum after the collision, so therefore big M v1 equals m plus m v2. We are looking for v2, so therefore v2 is mv1 over m plus m. Good, so what is v1? Well, as we worked out before, it's a kinematic. v1 squared is u squared plus 2as. Of course, it starts from 0, so that just gives us 2gs. But it's not quite that simple, because what is s? What is the distance that's fallen? Well, the distance of drop is going to be the height, of course, but it's going to be minus 2 lots of the amplitude, because we move from a lower point to a higher point. What I mean by that is 2gh minus 2a, where a is going to be mg over k, the force divided by, in other words, the extension. That's what a is going to be. So we're working our way backwards from the previous time. The previous time we added the two together. This time we're just looking for drop height, because it's accelerating for the drop height, not the total height of the box, just the time which it's dropped. Okay, so therefore v1 is going to equal 2gh minus 2mg over k rooted. We already know that h is 2mg over k, algebra, here we go, plus pi squared mg over 2k, so therefore we should call it, multiplying this side by 2 gives us 4mg plus pi squared, making a common denominator, which I've done. That's h. So now h minus 2mg over k gives me 4mg plus pi squared mg over 2k minus, I'll double that up, giving me 4mg over 2k. So that pretty much disappears with that bit. So v1 leaves me with 2g, and in the brackets, if this were the brackets, pi squared mg over 2k. Good. Just making sure I've caught all points. Take the 2's out. So that leaves me with pi squared g squared m over k rooted. And bolting it back into here again, my second velocity is going to be m over m plus 1. Sorry, m over m plus m. v1, which is m plus m pi g root m over k. And there is my velocity after the collision. Excellent. Okay then, so we've got that bit. What about the amplitude of the motion? Okay, so how do we go about working out the amplitude of the motion? Well, I think we ought to find an expression for the amplitude and work our way backwards from there. So, the amplitude of the expression amplitude, the expression, sorry, the velocity is equal to a squared minus x squared omega squared. And we're going to use that identity to find out the amplitude of the displacement. So, just moving that out of the way. Using that identity, we have just trying to see. Okay, how do we get to that identity? Is it worth just putting a little aside to say how do we get to that identity? X is a sine omega t. So then v, which is dx by dt, I'm just checking to make sure this is right, is omega a cos omega t. If we say that, use the identity that cos squared theta plus sine squared theta is equal to 1, then cos of theta is going to be 1 minus sine squared theta square rooted. So what I have here is the velocity is going to be omega, open brackets. This is x, because x is a squared minus x squared. Yes, that's right, because this is x. 1 is my amplitude, in effect, and that gives me cos. So a cos theta is going to be a minus a, which is, in effect, 1 squared a squared yes. Okay, so where do we go from here? Okay, omega is going to be the root of k over m plus m that we talked about before. X, two lots of the displacement, which is 2m g over k that we talked about. Remember, x was how far we've moved, two lots of the extension. A squared minus x squared gives me v2 squared over omega squared. v2 because that's what I'm going to take because I have an expression for that, which gives me m squared pi squared g squared over, just making sure I've got the right expression here, m squared pi squared g squared over m plus m squared by m over k and then so we have I've got my expression for v squared and then I'm dividing through by omega squared, so therefore multiplying by m plus m over k, which I've taken from here. But a squared is now this expression plus my x squared. So m squared pi squared g squared over m plus m. Let me take out one of those, m over k squared plus x squared, which is 4 m squared g squared over k squared by okay, and that gives me an expression for this as the square root of that, which gives me, let's factorize out the m and the g and the k. So the m, the g, and the k. So that leaves me with pi squared m plus 4m plus 4m over m plus m, because I can then, if I get a common multiple of this, I want to multiply by m plus m, which gives me an m plus m across the top. That's right. Whew. Okay, not easy, but there's a solution.